So I'm going to record this and post it on YouTube. Let me, okay, everybody's doing that. Give me some of my windows. Pardon my disorganization. I only found out recently that I was going to be doing this, so I haven't prepared. But I want to continue along with what we were doing before. Now that we're all set up, yeah, Caitlin, thank you for your flexibility. Um, how's everybody been doing? How has your first week of online classes been? I know you all were like very talkative last week when I covered your class, so please type stuff to me in chat and I will address it right away. Also, like last time, I know that Issa was commonly like unmuting her microphone and saying stuff. So um, please, feel free to talk. Yeah, Matt. I mean, I know you've been doing a lot of work for us too, teaching um, Physics 211. Thank you. If you ever get overloaded, let me know and we can adjust stuff. So any feedback for me for from last class? I mean, I plan on running this class kind of like last one, right? I will write freehand notes. Um, I will at the end capture those as a PDF and send them to Jack, and he can post them. Um, but is there anything that I need to know or do differently compared to last time to make this work better for you all? Okay. Thank you, Caitlin. All right, then I'll just kind of do the last thing, as closely as what I did last time. I will probably make some math mistakes because I have not prepared any of this. So let me back up a bit. What we did last time was we said, let's try to understand the Schrodinger equation. Let's try to understand how a particle's wave function varies in space and time when that particle is confined by some potential. So last time we said that our goal is to understand the variation in time and space of the wave function, psi of x and t, realizing that its squared norm tells us the probability density of finding a particle at any particular place in time and space. And my recollection, like what you told me last time, is that you've already seen the free particle solution to the Schrodinger equation. If a particle is moving in free space with no potential acting on it, that its wave function is given by that. Um, and then we moved from there to the Schrodinger equation. The Schrodinger equation is this big ol' beastie right here. And why the Schrodinger equation looks like this has to wait until you do like, yes, Danielle, thank you. Let me, okay, I'm going to have to go rejoin the 361 Blackboard to get Eva back in. Give me just one moment here. I'm going to have to like log in, but it's important that we not leave anybody out, so I'm going to have to log in a second browser. Uh, okay, let me now switch back to the one that I'm supposed to be in. Here we are. Okay, I'm back. Um, yeah, Danielle and Caitlin, I posted it back in the chat of the Physics 361 Collaborate. So where were we? Okay, this is the Schrodinger equation, the thing I have highlighted in green. And the reason it takes that form is going to have to wait until a treatment of quantum mechanics um, where we look at essentially an operator formulation of quantum mechanical things. For now, just take it as kind of a principle of physics that that is the Schrodinger equation. So what we did then was we said, let's put in a potential. What I wrote before was the Schrodinger equation for a free particle, one that is not confined by some potential. So then we said, let's now think of the Schrodinger equation here, where we add a potential. Somebody has raised their hand. Up. Ethan says this link is not working. Okay, let me try. Give me one moment. Got to make sure everybody can get in. Again, I'm sorry for the kerfuffles here. This is just because I didn't know we were doing this in advance, and I haven't been able to get a hold of Jack. So. All right. Hopefully that will work. Yep, okay, Ethan got in, good. Another message in chat there. Yeah, okay, we're good. So what we've done now is we've modified the Schrodinger equation to include a term that relates to the potential that our particle is moving in. And again, we're just going to have to treat this as a fundamental law of physics at this point. And now we're down to trying to solve this equation. So this is called a partial differential equation because it involves derivatives with respect to different things and a function of multiple variables. There are math department teaches entire classes in partial differential equations. They are not fun. I never took one, so I'm bad at this. But we're going to explore some techniques for solving this. And there's a particular kind of solution that is super interesting to us. And these are solutions that factorize. So solutions where the overall wave function, psi of x and t, is the product of a part that depends only on time with a part that depends only on position. And I've kind of color-coded this. Let me erase this scribble here. We'll come back to that. I've color-coded this where we've got the position-dependent things in blue and the time-dependent things in orange. And now what I'd like to do is I'd like to get all of the blue things and all of the orange things separated. So I've now divided through by blue thing times orange thing, and I wound up with this mess down here, which is where we stopped last time. So now what I'm going to do today is so the plan for today, you can't hear me. Is anybody else unable to hear me besides Ava? Okay, Ava, I'm sorry. The audio set issue is probably on your end. You might close your browser and reopen it. Unfortunately, yeah, Collaborate doesn't really play nicely with some sound settings. So the audio was working until you closed. Okay, Ava, one thing that you could do, if you want, is just go back in the 361 Collaborate session. I am now streaming audio to that one. So if you're still there, Eva, you'll get my audio through that one. Now I'm broadcasting in two places at once. Poke me again if you can't get it fixed in a few minutes, and we can give you some other suggestions. So, whoop, this is the window I want to hit Control D into. So now where we are is we need a way to make progress on this equation. Good, good. I'm glad you're with me. So now what we've got is we've got a, and I'm going to write this out kind of schematically. Whoops, not my box tool. We have a term describing spatial variation equals a term describing time variation. And in general, equating the way something changes in space with the way something changes in time, there aren't going to be very many solutions unless both of those things are always equal to a constant. So, because, I could vary space a little bit, I could vary time a little bit, and the only way those things could be equal is if they are both equal to constants. So what we get to instead is I'm going to just write both of these out separately. Minus h bar squared over 2m times this monstrosity plus the potential term that's just chilling equals a constant, and that's also equal to this part. So this may not seem like we've made much progress, but what we want to do now is digest each side on its own. We're going to digest the time part first, and we're going to understand what that means and what that tells us about our solutions, and then we're going to apply that knowledge back to the spatial part. And by the end of this, we're going to be having some pretty strong Physics 307 flashbacks for those of you who took Physics 307 with me. So, whoops. We're going to first look at the time part. So, what does it mean? I'll write this more smaller. What does it mean that a constant equals IH bar, whoops, so I'm sorry folks, phi, not psi, is the time-dependent one. d phi of t dt over phi of t. I just miswrote the wrong thing. Again, sorry, haven't prepared. So what does that mean? So fractions make me nervous, so I'm going to multiply both sides by phi of t. So this gives me c times phi of t equals, actually I'm also going to divide by ah bar. So this gives me 1 over IH bar c phi of t equals the partial derivative of phi, I keep doing that, with respect to time. So now I've got an equation that I have a fighting chance to solve because it's only got derivatives with respect to one variable. Yes, Caitlin. So the notation that we've chosen, going back here, um, looking at blorp, that piece, is we're representing the spatial dependent part with psi of x and the time dependent part with phi of t. um, all these Greek letters. I always joke that you can always tell the fraternity and sorority people because they know the uppercase forms of the Greek letters, but not the lowercase forms in lab classes. Like, that's something that is like a part of Greek life is learning the uppercase forms, but the lowercase forms I've never seen written in Greek life things. So this equation I've got a fighting chance to solve. And the way we're going to solve it is by thinking about what it means in words. So phrasing this in words, what this means is, not little arrows, I want to write text. When I take the time derivative of phi of t, I get back phi of t multiplied by c over I h bar. So do you know any functions where when I take their derivative, I get back that function multiplied by a constant? An exponential. Yep, exactly, Romeo, Danielle, Yanju. So this means that phi of t equals c over, whoops, nope, is some amplitude times the exponential of c over I h bar times time. Now, you'll often see this written in a different way because 1 over I is just minus I. So this is the same as e to the c yeah, minus c I over h bar t. So now we figured out what phi of t is. It's an exponential. But I want to compare this now to the solution we got for a plane wave, the solution you've already seen. So the plane wave solution that you saw here, there was a bare time dependence, right? The time dependence was this e to the minus I omega t. So here, if we compare that to what you've seen, which was psi of x and t, let me change colors. So this had, in the same way, t, this lets us identify omega as c over h bar. But you also know, at least I have it in my notes that you know this, like in what Jack sent me. Please tell me if this isn't something you've done, that for a plane wave, omega is the energy over h bar, which is equivalent to writing energy is h bar omega. Have you all seen that before? Yes, good. Again, I need your help for you all to tell me what you've seen before and like the notation you use and how the class has gone, because I'm just like, I've been dropped into this cold and I want to do the best job I can with you all in this class, but you got to help me do that. So thank you so much for your feedback, Caitlin. So what this tells us then, and this is a big deal, I'm going to write it in like the red and the biggest pen that I have. This tells us our constant C is just the energy E. So using that knowledge that we've just found out, then phi of t becomes a exp minus I energy over h bar times t. Or equivalently, a exp minus I omega t. So now we figured out something about the energy of our solution, and we've associated that energy with the frequency. So we have figured out what phi of t is. So I'd like to return back to the full thing now. Where I am now, Yanju has made a little face. Yeah, feel free to use the little like react things. If you want to tell me that I should, that you understand or that you don't, or that you're happy or you're sad or whatever, because I've got that up on the side of my screen. So where we are now is that this was, remember, the product of a spatial part with now the time part that we understand. But I want to stop now. Before I do any more math, we're all sick of math, right? Math is boring. I want to talk about what this means, because this is actually really profound. How many of you, if I say, like, when I talk about complex numbers, if I say a complex phase, do you know what I mean by that? Okay. Let me do a diversion and talk about how mathematicians and particularly electrical engineers like to think of complex numbers. So I'm going to draw a really big coordinate axis. I don't want it to be orange, I want it to be black or gray. So here is my big coordinate axis, and I'm going to graph complex numbers on this axis. Have you all seen this before? You have, okay. So Um, okay, so this is good review for some folks. So I can imagine, and here I'm using psi because I'm going to relate this complex number back to the wave function, but ultimately it could be any complex number. So if I put that complex number here, I can think of this as a point on ordered pairs where the horizontal coordinate is the real part and the vertical component is the imaginary part. So this is one way to describe a complex number, right? I could tell you its real and imaginary parts. But 99% of the time, when I have used complex numbers, I have not thought of them this way. So here I've got a complex number. It is that point, and I'll say one way to describe a complex number is to give you its real part and its imaginary part in Cartesian coordinates like this. But what would be another way I can describe that position on this coordinate plane? And as a hint, I'm going to draw in that arrow. How else could I describe that arrow to you if you're thinking about it like a vector? Angle and magnitude, yeah. This is just physics 211 stuff, right? I can describe a vector either by its horizontal and vertical components, or I could describe it by um, angle and magnitude. So Romeo, where the imaginary psi comes from is simply that from the beginning, when we've been manipulating wave functions, we have admitted the idea that they are complex numbers. We've treated them as complex numbers. So if like for instance, when we wrote down the Schrodinger equation way back here, um, there is, for instance, this I here. So the wave function in general is a complex number. And as a complex number, it's got a real part and an imaginary part. So for instance, I might write something like uh, psi is A plus BI, where here A is the real part and B is the imaginary part. I can't give you a good reason why wave functions are described by complex numbers. What I can tell you is that all of the cool stuff in quantum mechanics happens because they are. But the reason that your favorite creator deity has chosen complex numbers to be the fundamental mathematical thing in quantum mechanics, you'll have to ask that deity. So going back to Nick's insight, you could describe this in a more illuminating way. Um, Magnitude and angle. So that angle I'll write as theta, and this magnitude is going to be the magnitude of psi, like a vector. So let me ask you now another question. Have you seen Euler's formula before that says that e to the I theta is cosine theta plus I sine theta? You used it in class. Okay. This is where this comes in. Because what this means is that another way I can write this complex number, right? So if, let me do it this way. Whoops. So if psi is A plus BI, then the magnitude of psi is psi times psi star, which is A squared plus B squared. And the angle is going to be, well, let me put it this way. And A equals magnitude cosine angle. B equals magnitude sine angle. And here's the punchline. Psi equals a magnitude times e to the I theta. So is this something you've seen before? You have seen that. Okay, good. So when I say complex phase, no. Okay, good. So when you say you've seen this before, Matt, did you see that in this class or a different class? In 360. Okay, good. So this is good that we're doing this. So the way that complex numbers usually get used is by thinking about them as the product of a purely real magnitude and a phase angle with magnitude 1. So, what does this mean? This means that whenever you see something like this, whenever you see a term that looks like e to the I something, you should think this is a thing with magnitude 1. This is a thing that doesn't change the length of the arrow. It just rotates it around the complex plane. So that's the length of arrow, and this rotates arrow around the complex plane. All right, now that we've got that, let's apply that to what we have realized here. There is a way to do cut and paste with this software. I don't know how to do it with the stylus. So I'm going to rewrite it. What we have is we have that psi of x and t is some piece that depends on position times some other piece that goes like e to the I energy over h bar t. So, and there's an amplitude out front. So what this tells us is that solutions of this type, so solutions where we can separate out position and time, they have this form, and that means that the magnitude depends on position. Again, my notation is that position-dependent things are in blue, and this is just a complex phase angle. So, to see this, let me calculate that. Again, this is the probability density is psi squared. So this is going to be equal to a squared, well, let me write down one more thing first. So this is psi star psi, which is a star a, psi star of x, psi of x, that's the boring part, times e to the minus I e over h bar t times e to the plus I e over h bar t. And these pieces cancel. That's what we expect, right? We expect that something that is just a phase that's e to the I something doesn't affect the amplitude. So again, mathematical wisdom in physics is that anytime you see e to the I something, that doesn't change the amplitude, the magnitude of the complex number. So this is what we have arrived at now is a really big deal. So let's review what we did. We chose to look at solutions where the time and space dependence separate. We recognized that their time dependence was phi of t equals e to the I omega t, where omega was just the energy over h bar. And then notice that in this, in what I wrote up here, in this piece, whoops, that what's left doesn't depend on time at all. This is a big deal. It would be an even bigger deal if I was on the right tool here. There's no time dependence in the probability density. So these solutions have no time dependence in the probability density. Red, big type, exclamation mark, exclamation mark, exclamation mark. It turns out that almost always in quantum mechanics, what we are very interested in is understanding solutions with these properties. these solutions are called stationary states or normal modes. They are states that just vibrate. Yes, I will post all of these notes. Um, and I welcome feedback from you about how to make these notes more useful to you. Again, I'm just kind of winging it right now, based on broadly what I knew Jack wanted me to talk about. So again, their time dependence is just an oscillation back and forth. So have you all encountered the term normal mode before? In 360? Some people haven't taken 360. Um, Nick and Matt. Yeah, 307 gang, exactly. So in Physics 307, we emphasize thinking about the normal modes of a vibrating string an awful lot because this is a huge topic in quantum mechanics. So really, 307 was a backdoor preparation for quantum mechanics because the mathematics of things that just vibrate with a constant frequency everywhere and don't depend on position are the same as trying to understand the stationary state solutions in quantum mechanics. So what I'd like to do now is to show you an example. Because Blackboard Collaborate is a little bit squirrely, I'm gonna give me just one moment to try to make something work here. This may not work. I hope it will. Okay, all of my monitors have gone nuts. Stand by, I may have messed something up. I'm having to do this because Blackboard Collaborate is really annoying and doesn't, its screen share feature doesn't let me do a thing that I really want to do. You know what, we're just gonna... Okay, so can you all still see what you need to see on Blackboard Collaborate? It looks like you can. Let me just check to see that the recording is still going good. Okay, so what I'm going to do now is I'm going to switch to sharing my entire screen. Blackboard Collaborate will not let you share an entire screen if you have an external monitor connected. It doesn't do the right thing. So now you see the like tunnel of doom. So there is an analogy between stationary states in quantum mechanics and normal modes of a vibrating cavity. After all, in quantum mechanics, so if you have, say, a hydrogen atom, the normal modes are just or the stationary states are the ways that a wave can be trapped in that cavity with this property that probability density does not depend on time. But in the same way, if I have, say, a violin string, these stationary states are the normal modes of vibration of the violin string, the ways that it can vibrate, so that it just goes up and down, and you don't get things that vary in time. So let me give you an example. So here is a particular stationary state of a vibrating membrane. We'd like to make it a little bit higher resolution. Do we have enough CPU power on this little tablet to do n equals 80? Yes, so let me now go back to Collaborate for just a moment. Ah, darn it, show me my... Yeah, so Collaborate's being obnoxious and won't show me chat while I'm doing this. Yes, this will be on YouTube. So let me see if I can get all of the windows that I want up on screen at the same time. Yes, I can. So this is a particular stationary state of a vibrating membrane, like a drumhead. Again, this is the simulation that I just had handy. And my computer here is solving the wave equation, basically by doing things like you did in 307 for this shape. And notice that the behavior here is just motion up and down. And yes, there is variation in time, but it's just up and down. You're not seeing like position-dependent things. Let me show that now, an example of something that's not a stationary state. Whoops, what did I do there? Okay, so I've clearly broken something. Give me just a second. Again, wasn't planning on doing this today. I want to type center, radius, amplitude. We're going to try making the time step smaller, seeing if this fixes it. Ah, there we are. Sorry, folks. Again, wasn't planning on doing this today. Okay, now that we have that fixed, I keep touching the touchscreen. So here is an example of something that's not a stationary state. This is a vibration pattern where you see that, like, what's going on, the character of the vibration is different at different times. Where what I showed you before, the character of this vibration is constant in time. Yes, it goes up and down, but the character doesn't change. You could write this vibration as something like, you could write this in the form fix my touchscreen coordinates here. You could write this in the form y of position and time equals some amplitude that depends only on position times sine omega t. So this is then a stationary state. So this raises the question, what are some other stationary states for this system? Let me ask you all something. How many of you studied the hydrogen wave functions in or orbitals in high school chemistry, like 1s, 2s, 2p, all of those things? And you saw all those funny shapes? Did they ever tell you where those funny shapes come from? Or was that like, these look like balloon animals. Why am I looking at balloon animals? I thought this was a chemistry class. Yeah, they're the likelihood of the electron being in any given place. Exactly. Well, I can show you a comparison. So here are some other stationary states for the drumhead. So here's another one. Notice that the character of vibration here, again, is not changing. My computer program, I have pre-programmed in what the stationary states look like. It turns out their names are Bessel functions in mathematics. A Bessel function is like a two-dimensional sine wave. So this is a stationary state. So is this one. So you notice that in each of these stationary states, I'm getting increasingly more vibration nodes going from inside to outside. And along with this, as I get increasingly more nodal points in the vibration as I go from inside to outside, the frequency is going up, right? So these correspond, this is in 2D rather than 3D, but the analogy is better than you might think. So this is like the 1s state in hydrogen. I might be able to pull up a poster of what those the orbitals look like. So we'll see if Google will be kind to us. Here it is. Can I have a bigger version? Maybe. Yeah, I think this is the biggest version that we can get without like paying them for this. View image. Yeah, here we are. And now I need to shrink this down so we can see everything else at the same time. So notice that the 1s state, that's this blue one here in the top left, that everything is the same. The animation you're seeing is the stationary state. Again, I'm thinking about vibrations on a drumhead rather than waves around a nucleus, but the physics is the same. Now I'm going to switch to the 2s state. This is this one that's below it. Can you all see my mouse cursor as I point at things? You can. Okay. So now you're looking at this state. Notice that it's got a piece on the inside that moves differently than the stuff on the outside, and it's higher frequency. This matches what you know in hydrogen, right? You know that 2s has a higher energy than 1s. Now I can switch to the 3s state of hydrogen. And here it's got a tiny little piece on the inside, right? The innermost part of this. And then a ring on the outside that's vibrating differently, and then a large part on the outside that's vibrating differently than that. And you see that reflected in the 3s state, the picture here. But you know that there's more than the s states in hydrogen. So if we go down to the orbitals gallery, these over here, the ones that are in white and yellow, these are the p states. And notice that they have one piece doing something different than the other. And I can simulate those as well. So here is the vibrations on a drum equivalent of the 2p state in hydrogen. Notice that one side goes up at the same time as the other side goes down. So that is the 2p state. And I can continue this. So now look, before I do it on my computer, look at this one. This is the 3p state. So I've got one side going up, one side going down, but then an inner part that's opposite of that. That's also a stationary state on the vibrating drumhead. So this is 3p. I can go to 4p, which is, again, this funny one here. Notice how the vibration pattern you're seeing on the drumhead looks a lot like that. Now, this drumhead simulation, this is not, I'm not cheating here. I'm not like making it look stationary. This is the computer actually solving the wave equation for you in real time, like solving the Schrodinger equation in real time to make this animation. I can also go to the D states. So if you look in the orbitals gallery, look at this one, notice that the D states are divided into quarters. And that's a vibration pattern on the drumhead, divided into quarters. That's the 3D state. And as I go to the, I can go to the 4D state, which combines this. Now I am divided into quarters, but now I've got the inside doing something different than the outside, which looks like this state in the gallery of hydrogen orbitals. So let me kind of set in perspective what you're doing in Physics 361, and this is a project that will continue into your quantum mechanics class. The reason we're doing all of this is really we're paralleling the reason that quantum mechanics was so fascinating in the beginning, because it allows us to understand the atom. It allows us to understand the periodic table. It allows us to understand all of chemistry by telling us about the energy levels and the stationary states, they're the same thing again, in atoms. So first what we're going to do is we're going to understand the stationary states of a very simple example of an electron simply trapped in a cavity that it can't escape from, where the potential is infinite outside that cavity, but zero inside that cavity. And we're going to get practice in working with stationary states in one dimension. And then we're going to gradually work up to stationary states in more dimensions, and stationary states in potentials that are more complex. And the pinnacle of all of this, the goal really in essentially all of undergrad quantum mechanics is to, or like a, not the whole goal, but like a big stopping point is understanding the hydrogen atom and understanding the energy levels in hydrogen. So I have talked a bunch. I've shown you this thing. I've shown you examples of stationary and non-stationary states in my simulator. Do you all have any questions? Like, I've talked a bunch. What would you all like to know at this point? Oh, shoot. Let me get all my windows back. Can't click on that. So again, what you're seeing here is not a stationary state. Did I show you the f orbital? I didn't, but I can. So the f orbitals here, this is the 4f state, this one that is green and white, Ethan. And it is one where this is cut into 6. So if I tell my program to show me the 4f orbital, notice that now this is cut into 6. And I can go to the 5f orbital, and notice that as I go to higher and higher numbers, the oscillation frequencies get faster and faster. And this is what you expect because, remember, energy is h bar omega, so the higher the frequency, the higher the energy of the state. Again, this is not quite the same because it's in 2D rather than 3D, but the essence is the same. I think the highest one I have like pre-programmed in here is like that one. Which I don't even know what that is. So let me ask you all for feedback now. Did you all find this cool, like seeing these visualizations and the connection to chemistry? Oh, the compression has gone haywire on your end. Okay, I will, because I've never taught modern physics. I would love to teach this class. So I'll keep that in mind as something fun to do. I actually sometimes do this in Physics 211, because this is something that you can understand in Physics 211. You can understand vibrations, and we relate them to atoms. All right, so let me now try to reset all of my displays. To get my multiple monitors turned back on. So that's that. Stand by for 15 more seconds. I'm so sorry. I appear to have lost connection to one of my monitors. I need to do this just to get my my notes back up and working well. Okay, stand by for one more moment. I am so sorry. We are still recording, that's good. Collaborate goes over there. Notes go on the thing with the touch screen. Now I can share. Okay, so you see my notes again. Okay, so I'm just getting all my stuff reset. Get chat up. Okay, so returning to our mathematics, let's talk about where we are now. So now that we understand what our solution looks like, so I'm going to say recall. Our wave function, depending on both space and time, was this piece, the piece that depended on position. Make sure I have the form right. Yes. Was h bar squared over 2m times the second derivative of the spatial part plus this potential piece and that was equal to a constant. Whoops. Sorry. This was our spatial piece of the wave function, and the whole thing, depending on position and time, was the spatial part multiplied by this piece that depended only on time, exp minus I energy over h bar times t. But we can't make any more progress now without knowing what the potential is. But where did A go? Good point. So A is just a normalization constant, because remember, if you look at this form up here of psi of x, I could multiply psi of x by a constant, and the same thing still works. Actually, wait, this was up here a constant times psi of x, which we've identified as the energy. Sorry, I'm making mistakes just because I didn't prepare enough, or didn't prepare really at all. So this was the equation we had, this guy, for the spatial part. And notice that I have this term in blue, which is the space derivatives, position space derivatives of psi, plus a piece that depends on the potential, equals the energy times the wave function. So you can already tell that we're going to have, in things with different stationary states, each one is going to be associated with a different constant energy. Another way to think of stationary states is wave functions that have a constant, well-defined energy. But thank you so much for reminding us of the constant A, because that brings up a couple of constraints on psi, and I think this is the last thing I'll talk about in the last 8 minutes. There are two constraints on psi that are required for a meaningful solution. The first one, I should say psi of x, because here we already know how the time dependence works, and here we're just thinking about the space dependence to get the stationary states. So the first one is, remember that psi of x squared norm is a probability density. Then what that means is that the integral over all space of psi of x squared dx must equal 1. Because we've got to find the particle somewhere, right? If we're calculating something that tells us the probability of finding a particle in some place, it's got to be somewhere. So this is called normalization. And since psi of x has that constant a in it, choose a so that this is true. So our constant a up here, that one that I forgot and that you reminded me of that I had to put in later, the one that I've just highlighted in red, the reason I forgot it is because we often don't think about it that much. Oh, come on. Because this is just set by the need to make the wave function normalizable. What this does mean, though, is that if this integral is infinite, right, if when I do that integral without the constant in, if I get an infinite answer, then no constant a will make the normalization come out to be 1. And those, that tells you that it can't be a physical solution. One way to think of this is if psi of x extends out to infinity, if it's a wave function that has some probability of finding the particle all the way from minus infinity to plus infinity, then that integral will probably be infinite and it won't be normalizable. So stationary states usually correspond to bound states, where the particle is confined in some region, like a hydrogen atom or a potential barrier on both sides of some kind. The other one is, notice that h bar squared over 2m, second derivative of psi, x psi of x equals e psi of x. This has got a second derivative in it, right? Which means that this had better not blow up. What this means is, so for the second derivative of something to be finite, so that minus sign, yep, you're right. I never can remember that. So yeah, let me fix that minus sign. Thank you, Matt. So for the second derivative to be finite, what must be true? That's finite only if both psi of x and its first derivative are continuous. Continuous. Unless the potential is unless the potential is infinite. That's a corner case that we will meet a little bit later. Yeah, James. So exactly. If the thing is moving very fast or accelerating very fast, then that diverges. So we've got 2 minutes left. You okay, James? Does that make sense? Okay. So let me tell what we're going to do next in our last minute. What we want to do is remember we have to think of a particular potential. So the plan coming up is to imagine the simplest potential we can think of. So this is one where we're going to put x there and v of x there. So we're going to imagine a potential that is v equals infinity for x less than 0. V equals 0 for x between 0 and L, and then again v equals infinity for x greater than L. So essentially we are confining a particle in a box of width L and calculating the stationary states of that. Spoiler, they're exactly the same as the normal modes of a guitar string. So that's the time for our class. I am sorry about the tech things and the disorganization. Um, Hopefully Jack will be back on Thursday. If not, well, regardless of which one of us teaches, I will continue actually working through and figuring out what the normal modes are for a particle trapped in this potential. If there are any questions, please feel free to ask me. I don't have something I have to do right after this. Otherwise, I'm going to save this PDF and I will get it to you all. Thank you so much for your patience, your attention, and bearing with me. And any feedback you have about this will be very helpful and will help me improve any other online classes that I do, which is a lot of them. Alrighty, I guess there are no questions, so I will hop off of Collaborate and I will see you all later. Thank you all for your hard work.